Hello everyone. Okay, last time we got to the point when we realised that the only way to describe the orbits of electrons is not going to be an easily imagined classical planetary-like orbit, but we need to use a quantum mechanical framework. In particular, the orbits or orbitals are described by a mathematical function, a wave function. Schrödinger's equation allows us to calculate the shape of the allowed wave functions, and it also connects each wave function with an associated energy for that function. Now, I said that there are many different allowed wave functions. We can identify and label the different solutions to Schrödinger's equation by a series of quantum numbers. In fact, we will need just 4 types of quantum number to describe all of the properties of an electron in an atomic orbital. These quantum numbers, or labels, are n, l, m subscript l, and m subscript s. For each electron in an atom, there is a unique set of values for these 4 quantum numbers. We use 3 of these values, n, l, and m subscript l, to identify each orbital. The m subscript s quantum number relates to a property that is intrinsic to each electron, and we'll come back to this. The type of value that each quantum number is permitted to take is very limited. I will now take you through each of these, what values they can have, and what each one means. So, actually we've already met the first and most important quantum number. It is n, and it is called the principal quantum number, and it can only take values that are natural numbers. That is, it can be 1, or 2, or 3, or 4, etc., etc. The principal quantum number n is the same n that we saw in Bohr's model of the atom. Bohr assigned a value to n for each of his different orbits, with n being 1, with n equal to 1 being the orbit that is closest to the nucleus, and the one that has the lowest potential energy. The larger the value of n, the larger the value of the atomic radius, according to Niels Bohr. In our case, n also determines the size of the orbital. The orbital with n equals 1 is the smallest, and as n gets bigger, the orbitals get bigger. Roughly speaking, n is associated with the periods of the periodic table. The first period, which contains just hydrogen and helium, has atoms where the outermost electrons are in an orbital with n equal to 1. The second period, from lithium through to neon, has electrons in a larger orbital with n equal to 2, and so on. This actually matches very nicely the size of atoms. It turns out to be very difficult to measure some exactly comparable size for all atoms across the elements of the periodic table. But that's another story. Certainly, as we go down any group, the size of atoms increases, usually by very significant amounts. And while we go across a period, the size of atoms tends to decrease by a small amount from neighbouring element to neighbour, but this trend is cumulative, and so the difference between elements at either end of a period is very substantial. We've already seen this behaviour in the lanthanide elements. Anyway, going down a group, the reality is atoms get bigger, and in our model, as we go down a group, we are using orbitals with successively bigger values of n. Now, before I show you an orbital, I have to introduce a second quantum number, L. L is known as the angular momentum quantum number. It actually defines the radial spatial distribution, or, to put it more simply, it defines the shape of an orbital. The permitted values of L are completely constrained by the value of n. The rule is, for a given value of n, L can take integer values ranging from 0 up to a value of n minus 1. That means for n equals 1, L can only take the value of 0. But for n equals 2, L can take the value of 0, or it can take the value of 1. For n equals 3, L can take either 0, 1 or 2. And for n equals 4, L can take values of either 0, 1 or 2 or 3. You get the picture. Now, partly for historical reasons, partly because we're chemists, not mathematicians, and so it helps us to remember, we add in a letter code when talking about the values of the angular momentum quantum number. I mean often, instead of saying L equals 0 or 1 or 2 or 3, we would use the letters S, P, D and F. I know that just sounds confusing, so let me try and say it in words. Let me try and say it out in words. The wave functions where L equals 1 are called s orbitals. The wave functions where L equals 1 are called p orbitals. The wave functions where L equals 2 are called d orbitals, and the wave functions where L equals 3 are called f orbitals. Wave functions where L equals 4 are called g orbitals, and wave functions where L equals 5 are h orbitals. It doesn't stop there. It just goes up alphabetically after that, and we don't usually need to go there. So let's get into it. Let's have a look at the first wave function. We can symbolically write it down with the Greek letter psi. Taking the lowest value of n equals to 1, that means L must also equal 0. There is no choice in this value. And that means if L equals 0, we're talking about an s orbital. In fact, as the first s orbital, it is the simplest of any orbital, and so we can label this wave function with the values of n and L, but more commonly we would replace the value of L with the letter code. So this orbital becomes the psi 1s orbital. So this is what the 1s wave function looks like. It's very difficult to show. Psi 1s gives a value for different coordinates in space, different x, y and z coordinates. Remember that psi, the wave function, is a thing called a probability amplitude. When we square the wave function, or square the probability amplitude, we get the probability of finding the electron. Here we represent higher values by a brighter colour. The lowest value, well 0, is black. I think it's more helpful to think about this as a one-dimensional plot. The wave function is spherically symmetric. So it doesn't matter where we start. But let's imagine taking a little box with dimensions dx by dy by dz and ask what is the value of psi inside the box as we move it from one side to the other, passing through the atomic nucleus at the centre. We would have a function that looks like this. The values are always positive. It is lowest, meaning close to 0, far from the centre, and it reaches its highest value at the nucleus. You have to try and imagine a spherical cloud with the greatest intensity at the nucleus. The probability amplitude is not the probability. To turn this into something meaningful to us, we square the probability amplitude to give us a function which tells us the probability of finding the electron in different places. Let's do the same thing, moving from one side of the atom to the other to give us a very similar looking function. Points to note. The value is positive everywhere. That's good. You can hardly have a negative probability. Perhaps surprisingly, the place where there is the highest chance of finding an electron is at the nucleus. Also, this probability gradually decays, asymptotically, to 0. It never actually reaches 0 as we move away from the nucleus. And this presents us with a problem. Where is the edge of the orbital? How are we going to be able to say how big an atom is? Well, here's one way. We can use this little box to represent a point, and say, what is the probability of finding the electron in the box? Or we can reframe the question. So we could say, what is the shape of a surface that encloses a combined total probability of finding the electron that adds up to 99%? That's a good way to do it. We've got a sphere. Inside the sphere is a 99% chance of finding the electron. Outside the sphere is a 1% chance of finding the electron. That seems fair. That this sphere encloses the orbital mostly, and that's quite helpful. But my 99% of the atom is a rather arbitrary number. I might have been happy with just 90% of the atom, and clearly that would have given me a sphere with a smaller radius, and just as 99% boundary surface would give me a bigger sphere. There's another way to frame the question about where is the electron. We know this wave function is spherically symmetric, so all directions look the same. So we could ask, what is the probability of finding the electron at some distance r from the nucleus? Actually, we need to sample with a finite element to obtain a meaningful probability. So imagine a shell of radius r and a thickness delta r. Actually, the volume of such an element increases as r increases linearly. That is, the volume gets bigger at a faster rate than the radius gets bigger. Now, the probability of finding an electron at distance r from the nucleus looks like this. This function has a peak, which is approximately the average distance for an electron from the nucleus. So this is one measure of the size of an atom. The position of the peak is the most likely distance for an electron from the nucleus. However, while this is independent of my arbitrary probability cutoffs, the position of the peak gives us a sphere which is very much like the 50% probability boundary surface, which looks like the size of, half of an atom. You begin to see the problem we encounter in trying to do the simplest things, like size an atom. And worse, this is what happens when we have just one electron. This is the simplest atom. Okay, let's have a look at the next wave function. When n equals 2, L can take values of 0 or 1. When L is 0, we have another s orbital, and we can represent this one with the psi2s wave function, and here it is. Again, it's spherically symmetric, as are all s orbitals, but what is different is that the value of the wave function, or the probability amplitude, if you like, is positive in the vicinity of the nucleus, but at a particular distance it passes through a value of 0 and becomes negative. Let's have a look at that as a one-dimensional function by taking a path from one side of the atom to the other. Okay, maybe let's convert that into something more meaningful. Square the function to give us the probability distribution. Remember that a negative times a negative is a positive, so the probability P is positive everywhere, except where it's 0. And there is an inner sphere where this is true, a sphere where the electron is forbidden. Don't worry, in quantum mechanics, of course, the electron is allowed to jump the gap. So we've seen the 1s and a similar 2s orbital. What about the 3s orbital? Perhaps that was predictable. There are now 3 changes in the sign of the wave function as we move from the middle to the edge. I've got 2 more points to raise here. 1. These orbitals are all getting bigger as the value of the principal quantum number is getting bigger. The second point is, although we have changes in the structure of the wave function in the inner part of the orbital, this is mostly incidental. How an atom reacts or interacts with others is mostly dependent upon the outermost atom. Well, 1s, 2s, 3s, 4s, 5s and so on. The outer parts of all these orbitals look essentially the same. That's why all the atoms in the s block behave very similarly. Now, what about the orbitals where the angular momentum quantum number L equals 1? In other words, what about p orbitals? The simplest p orbital are the 2p ones. What does that look like? Well, okay, two colours represent two signs of the wave function, positive and negative, and clearly a surface where the value of psi is 0 at the interface between these two coloured regions. You will also notice that there's a direction and orientation to this orbital. So let's take that transatom ride and see how the probability amplitude changes. We can do the same thing with the probability. The nodal plane passes right through the nucleus. Unlike s orbitals, there is zero chance of finding the electron in a p orbital at the nucleus. Time to introduce the third quantum number. Known as the magnetic quantum number, m subscript L is strongly related to L, the angular momentum quantum number. Effectively, m subscript L defines the orientation of a wave function. The allowed values of ml are constrained by the value of L. ml can range from -L to +L in increasing in integer units. So if L equals 0, ml can only be 0. If L equals 1, ml can take three possible values. ml could be -1, or ml could be 0, or ml could be +1. For L equal 2, ml ranges from -2 to +2, and for L equals 3, ml ranges from -3 to +3. Each of these possible values for ml is another solution to Schrödinger's equation, that is, another orbital. So you can see that there is only one s orbital, but there are always 3 p orbitals, there are always 5 d orbitals, and there are always 7 f orbitals. Now, I'm not going to sugarcoat this, but there's a bit more mathematical complexity that is always encountered in orbitals where the m subscript L value is not 0. Let me show you. So for the quantum number n equals 2 and L equals 1, there are 3 possible values for ml. So we can find 3 orbitals. There's psi 2p minus, psi 2p0, and psi 2p plus. We've already met the middle one here. This is where ml equals 0. But for the plus and the minus, the wave function is a little bit more complicated, by which I mean complex, in a mathematical sense. I mean each point in space is characterized by a real and an imaginary component, as if the visualization of a cloud in 3 dimensions wasn't difficult enough. It's okay though. As a mathematical trick, the psi 2p0 is aligned along the z-axis and becomes, and we can relabel this the psi 2pz orbital. The two complex functions can be combined in such a way as to eliminate the imaginary component, producing a px and a py orbital. So together, for L equals 1, we have a set of 3 orbitals with lobes, each directed along the x-axis, the y-axis and the z-axis. Because they all have the same energy, we call all of these orbitals degenerate. So what about the p orbitals as you increase the principal quantum number n? Well, we've met the 2pz, but there's a much bigger 3pz and a bigger still 4pz. Like the s orbitals, their shape and character on the outer parts of these atoms are very similar throughout, and this is in part responsible for their characteristic chemistry. Okay, what about other values of L? Looking at the maximum value of L for each allowed value of n clearly reveals some patterns in the shapes of these orbitals. The 1s orbital had no nodal plane, the 2p orbital has one nodal plane, the 3d orbitals, when L equals 2, have two nodal planes, and the 4f orbital has three nodal planes. In fact, we need to do the same sort of trick for the L equals 2 solutions, where we take some combinations of the mathematically complex functions to eliminate the imaginary components and get a new set of 5d orbitals. So where are we now? When n equals 1, there is just one sort of orbital. It is the 1s orbital. When n equals 2, there is now a single s orbital and 3 p orbitals. So four orbitals in total associated with n equals 2. When n equals 3, we can add in an extra 5 orbitals. And when n equals 4, we have one s orbital, 3 p orbitals, 5 d orbitals, and an extra set of 7 f orbitals. When there is only one electron, as in the case of hydrogen or any hydrogenic atom, such as helium plus, then the energy of the wave function depends only on the value of n. Here, the energy of the 2s and the 2p orbitals are exactly the same, and we can put the electron for the hydrogen in any orbital. But clearly the lowest energy, the most stable, or the ground state configuration, is obtained by putting the electron in the lowest, energetically, the lowest available orbit. Now, let's revisit the periodic table. In the s block, the outermost orbit is an s orbital. In the p block, the outermost occupied orbits are p orbitals. And the 10 columns of the d block correspond to the filling of the 5d orbitals, and the f block corresponds to the filling of the f orbitals. Since each sequential atom has one more electron, it really looks like you can only get 2 electrons in any one orbital. Okay, this is the last stage. I need to introduce Wolfgang Pauli. Pauli realized that electrons have this fundamental property that they cannot occupy the same physical space. We know that we can get 2 electrons in one orbital at a time, and that led Pauli to propose the last quantum mechanical quantum number. He said that electrons have a spin angular momentum that is characterized by a spin quantum number s. S is very much like L, and has a related quantum number called m subscript s. The m subscript s follows the same rules on what values it can take. It depends upon the value of s, and it ranges from -s to +s, going up in integer units. In the case of an electron, s equals 1/2. That means that ms can only take values of -1/2 and +1/2. These define the orientation of the electron's spin angular momentum, put simply, whether it is spin up or spin down. So in filling up orbitals, because there are only 2 possible values for the electron spin up or spin down, we can only put 2 electrons in any one orbital, and so keep all quantum numbers with different values. You can see how we get this expression of pairing the electron spins, since there must be one up and one down in each orbital. Okay, end.